Hello everyone, my name is Harnit Saini. I am assistant professor in Ajay Kumar Garg Engineering College. The topic of today's discussion is CPU scheduling. Basic concepts under CPU scheduling is why we do CPU scheduling. Because we have only one CPU and number of programs, those who want CPU services for them to be executed properly. So the basic necessity of CPU scheduling is that maximum CPU utilization obtained with multi-programming, because we have multiple number of programs. So we should use the CPU in that way that our program's waiting time should be minimized, right? And the CPU utilization should be maximized. CPU should not remain idle for longer time. CPU input-output burst cycle. Process execution consists of a cycle of CPU execution and input-output wait. And when a program runs, it requires the CPU time also, and it also spends time in input-output work, right? Then the process which consists of this cycle of CPU, when it is using the CPU, at that time we say it's the CPU cycle, and when it is waiting for the input output to be done, then it is the input output wait. Now our main concentration here is CPU burst distribution. It should be done in a way that all programs are run in a proper way and every job is completed in time. Now see here, these are when the program arrives, it's load, store and read from the file. This is all done by the CPU. Then it goes for the wait for input output, then it is called as input output burst. Then store, increment, index, write to file, these all functions are done by the CPU, and then it will again wait for input output device. Whenever the work is done by the CPU, then it is called a CPU burst, right? And when they are waiting for the input output device, then it is called input output burst, right? So the life cycle of a program consists of burst time cycle like this. Now what is a CPU scheduler? It selects among the processes in the memory that are ready to execute and allocates the CPU to one of them. Now we have a pool of programs to be run by the CPU. So one program has to be selected for which the CPU is to be given to it, right? CPU scheduling decisions may take place when a process switches from running to waiting state, switches from running to ready state, switches from waiting to ready state, and again terminates. Schedules can be preemptive and non-preemptive. Now, when are the decisions to be taken that which process will take the CPU is when a process is running, right? And it will go to the waiting state. Some other process has to come and take the CPU. Then from running to ready state, right? It was running. It was not going to input output. It was running, but for some reason the CPU is snatched from it. Means the CPU is taken from him and it is given to some other job, right? So it will move from running state to the ready state. From the waiting state to the ready state. Now it was waiting for the input output. Input output is done. Now it will go to the, now it is waiting for the CPU. Then it will go for CPU waiting. They have to go into the ready queue, right? Then for termination also, the CPU is required by the program. Now schedules can be preemptive and non-preemptive. Preemptive schedules are those in which we can interrupt the CPU, we can take the CPU in between, we can stop the job in between. But non-preemptive schedules are those schedules which once the CPU is allotted, the whole job is done and then only the CPU is taken from it, right? What is the role of dispatcher? Dispatcher module gives control of the CPU to the process selected by the short-term scheduler, and now from the jobs which we are kept in, which are there in the ready queue, one job is selected from which the CPU will be given. Now what the dispatcher will do, it will take that job and gives the control of the CPU to that particular job, right? Then the steps which are involved in this dispatching is switching context, switching to user mode, jumping to the proper location in the user program to restart that program, right? Switching the context means whatever we are assuming that job, some state is stored, if some logs are stored, which tells us what process is already done for that particular program or what particular schedule, right? And then we have to resume back that process. Then this context switch will switch or will resume all the things, will start the job again. And then it is switched to the user mode. And then from jumping, now some part of the program is already computed. Now we have to start from where it has not done already. Then that context switch will tell from where the program has to be started again. Dispatch latency, time it takes for the dispatcher to stop one process and start the another process. Now, when the CPU is taken from one job, the stages, the variables, the state is recorded, and then the other process which is to be loaded in for the CPU, which the CPU control has to be given to the job, we have to resume all the stage which we have stored earlier. When this one is stopping and other is starting, the programs and the state of that program, for the one program you have to stop and the other program you have to start. So this is the job of the dispatcher for the program. Now the scheduling criterias, we have to make a schedule in a way that the CPU utilization is maximized, right? CPU is not idle for longer time. We have to make sure this. And we have to increase the throughput, right? Throughput is the number of processes that complete their execution per time unit. Turnaround time, amount of the time to execute a particular process. When a process enters and when it terminates after completion, the total time spent by the particular program is the turnaround time. Waiting time, amount of time a process has been waiting in the ready queue, right? Response time, amount of the time it takes from when a request was submitted until the first response is produced, right? First time when it runs, it at the time at which it first gives the first response is the response time. Now, the optimization criteria, we have to maximize CPU utilization, maximum throughput should be there, turnaround time should be reduced, waiting time also should be reduced, and response time also should be reduced, right? Now, let's discuss the first scheduling algorithm, that is first come first serve scheduling. In the first, when the operating systems were created, the scheduling which was followed by default is first come first served. Now let us consider three processes, P1, P2 and P3, right? P1 requires CPU for 24 units of time, right? And P2 require only for 3 and P3 also require only for 3 units of time. Now what will happen? Suppose the processes arrive in this order, P1, P2 and P3. Let's make the Gantt chart. We will start the job at 0, right? And P1 will go on and will be completed after 24 units of time. Then P2 will start, it will complete till 27 and P3 will complete at 30. Now, the waiting time for P1 is 0 because it arrived first and it was started as that. P2 has to wait 24 units of time because it came with P1 but it has to wait for P1 to finish and then it will start. P3 has to wait 27 units of time because here it has to wait for the completion of P1 also and P2 also. Now the average waiting time is 0 plus 24 plus 27 divided by 370, right? Now what has happened? Suppose we change the order now, right? We first run P2 P3 and then P1. Right? What we have done, the longer process, we made the longer process to wait and we made the shorter processes to run first. Now, what's the time? P2 has not to wait, right? So, the waiting time of P2 is 0 because P2 is not to wait. P3 has wait 3 units of time, right? This way. And P1 has wait 6 units of time. 6 units, right? Now, the average waiting time is 6 plus 0 plus 3 divided by 3, we got only 3. In first case, when it was P1, P2, P3, we got average waiting time as 70, which is much larger than this 3. So, this is much better than the previous case. This is called a Conway effect. When shorter processes are waiting for the long processes to complete. Now, to overcome this problem, where we can reduce the waiting time, we introduce some more algorithms so that we could use the CPU efficiently. So, the next scheduling algorithm is shortest job first scheduling, right? Means we will execute that job which is shorter first and then we will execute the longer one afterwards. So, it can be of two types, non-preemptive and preemptive, right? Non-preemptive means once the CPU is given, you will not stop in between, it will complete fully, right? This is F here, shortest job first, right? Preemptive scheduling, in which we can stop in between if the other process arrives which is shorter than the remaining time of the first one, we can stop in between, right? Then that is called preemptive or shortest remaining time first, right? Now, SJF is optimal and it gives minimum average waiting time for a given set of processes. We have found that this process, this way of scheduling is better than first come first served. Now, let's take an example. There are 4 processes P1, P2, P3 and P4, right? P1 arrived at 0 units of time, P2 at 2, P3 at 4 and P4 at 5, right? And their burst times are 7, 4, 1, 4 respectively. Now, we will start first the non-preemptive one. We will start at 0. At 0 arrival time, we have only process 1, right? So, we have to start P1. So, P1 will start and it will complete its burst time 7 and it will be done, right? Then, after that, when we reach 7, these all jobs have arrived by that time, right? Among these 3, which is the smallest now? With this P3 is smallest because it has the shortest burst time. Then we will execute P3, right? P1 is complete, P3 is complete, we are left with P2 and P4. Both have the same burst time, so we can start with P2 because it arrived first, right? P2 will be executed for 4 units of time and then P4 are 4 units of time. Now, what will happen? The average waiting time for P1 is 0 because it arrived at 0 and it started at 0. Then it has not to wait for any time. Now, P2 arrived at 2 but it started at 8. So, how much time it has wait? 8 minus 2, 6, right? Then P3 arrived at 4 and started at 7. How much time it waited? 7 minus 4, 3, right? P4 arrived at 5 but started at 12. So, how much time it waited? 7. This is the way and we will divide by 4 and get the average waiting time. Now, if we want to calculate the turnaround time, right? So, turnaround time will be for P1, turnaround time will be the waiting time, that is 0 plus the burst time 7 is equal to 10, right? For P2, what will be the turnaround time? waiting time is 6 and the burst time is 4, 10, right? And for P3, waiting time is 3, burst time is 1, 4, right? P4, waiting time is 7 and burst time is 4, right? And what will be the, this is the turnaround time for each process. And if you want to calculate the average turnaround time, you will calculate this, total it, okay, and this will, you will get total turnaround time, right? And if you want to calculate average turnaround time, this will be a turnaround time divided by number of processes, right? Now we start with preemptive shortest job first, or SRTF, shortest remaining time first. Now you see the scenario. There are 4 processes, P1, P2, P3 and P4. Arrival time 0, 2, 4 and 5. Burst time 7, 4, 1 and 4, right? Now, at 0, we have only one process, P1, we have to start that. Next arrival time is 2. So, we will execute P1 till 2 and check, is there any process which is shorter or not? Then P1 has executed 2, so remaining time is left 5. So, for 2 units of time it has executed and 5 units of time is left. Now, we compared it with P2 at that time. P2 is 4 units of time and this requires 5 unit time. So, P2 is shorter than P1. So, we will start P2 here, right? Now, next arrival time is 4, right? We will execute P2 till 4, right? Means 2 units of time we have executed. We are left with 2 units of time, right? Now, we saw at 4 that P3 has arrived, which has arrival time only 1, which is the shorter of these 3, shortest. So, we will execute P3 now, right? P3 is executed till the next arrival time 5, 1. So, this is complete. So, this is complete now, okay? Now, at 5, we have all the processes, right? We are, now P1 is left for 5 units of time, P2 is left for 2 units of time and P4 is left of 4 units of time. So, which is the shorter now? Which is shorter is P2. P2 is for 2 units of time, we will execute P2. Now, this is also complete. We are left with P4 and P1. Out of these two, P4 is shorter, so we will execute P4. It is also complete, right? And P1 will execute whatever is left, we will execute P1. Now, how to calculate the waiting time here? Now, see, P1 has arrived at 0, it started at 0, well and good, but it stopped at 2 and restarted at 12. So, this is the time where P1 has waited, right? So, it is 11 minus 2, 9 milliseconds it waited, right? P2 arrived at 2, but started at 2, okay, no waiting here, but it stopped at 4 and restarted at 5. So, this 1 unit of time it waited. Then 1 unit of time is the waiting time of P2. Now, see P3. P3 came at 4 and started at 4. So, it does not wait. So, the waiting time is 0. P4 came at 5 and started at 7, right? 7 and it is completed when it started. So, here further it is no waiting. That means it waited from 5 to 7, that is 2. 2 units of time it waited. So, total is this divided by 4, right? Then 11, this is 9 plus 1, 10, 12. 12 divided by 4 is equal to 3, right? Now, the priority schedule. Priority scheduling is also a type of scheduling where we execute the higher priority jobs first. Now we will not see the burst time, or not we will see how much time the CPU is required. We will see the priority, even if it is longer than the other process, right? The priority is a number associated with each process. The CPU is allocated to the process with the highest priority. Means we have to pick the job which has the highest priority. Smallest integer implies highest priority. It may vary from book to book. In some books, it may be lower, greater integer than highest priority. Maybe this will be given in the question, right? Now it can be also with preemptive and both non-preemptive, right? So, like we did shortest job first with the both, priority can also be done. If we compare shortest job first and the priority, then we can say that the job with the shortest burst time has more priority than the other jobs, right? SJF is a priority scheduling where priority is the predicted next CPU burst time. Priority is equal to starvation minus lower priority process may never execute. Now there can be a problem in priority schedule. Problem is called starvation, in which every time a process wants to execute, a higher priority job comes, right? It always goes on waiting and waiting and waiting, right? So this situation is called starvation. Now we can solve this problem with the concept called aging. If a particular process is being starved for some number of time, then we can increase its priority by 1. The aging factor we can add. If age means if the process is older, much older to certain limits, then we can increase its priority so that it can rise in the priority and some or the other time it be executed. Round robin process. In the round robin, we give the CPU for a certain quantum of time for every process, right? For example, the time quantum is 2 milliseconds. We will give to every process for 2 milliseconds only, not more than that, whether it is executed fully or not. Okay, we have to do preemption in this, right? Each process gets a small unit of CPU time that is called a time quantum. It is usually 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added to the end of the ready queue. What happens when we have processes using the CPU and the time quantum is completed, then the CPU is taken away and the process is added again in the ready queue. If there are n processes in the ready queue, the quantum is q, then each process gets 1 upon n of the CPU time in chunks of at most q times unit at once. No process waits more than n minus 1 q time units. Now here we solve the problem of starvation and aging. Now here every process, whether it comes late, whether it is of low priority, whether it is a shorter or longer, it will get CPU after some or the other time when the quantum arrives. When its chance arrives, the CPU quantum will be given to every process, right? Performance queue large, that means FIFO means first one who that arrived will get the quantum first, right? Because small q must be large with respect to context switch, otherwise overhead is too high. The time taken in context switching should be much smaller than the quantum, so that the processes are doing some work rather than busy in context switching only, right? Now let's take an example. We have a round robin with the time quantum of 20 units of time. Now we have processes P1, P2, P3 and P4, right? They have burst time 53, 17, 68 and 24. So for first 0 to 20, P1 will go because it will arrive first, then P2, P3, P4, 20, 20. Because this is smaller than 20, it will go for only 17 milliseconds or 17 unit of time, right? then P3, then P4. Okay. After that, that particular CPU will be preempted from that. Now, here P2 is complete because the burst time is less than the time quantum. Then again P1, P2 is completed, so it is gone, P3, P4, right? Then P4 is also gone because in first lot it got 20 and in second lot it got 4. So it is completed. So we are left with P1 and P3, P1, P3, P1 is also completed and then we are left with only P3 here. So again the quantum will given to the P3 only. Typically higher average turnaround time then is there, but better responses. Now multi-level queues, right? Ready queue can be partitioned into separate queues, that is foreground or background processes. Each queue has its own scheduling algorithms, like foreground processes will have round robin, background will have first come first served. This way we can, in multi-level queues, we can have various algorithms. Scheduling must be done between the queues. First, the processes are scheduled within the queues and then each queue will have the other algorithm. Then fixed priority scheduling, that is serve all the foreground processes then from background processes. Again, the possibility of starvation can be there. Again and again the processes are arriving that are in foreground queue. Background processes are not getting the chance. Then the time slice, each queue gets a certain amount of time, CPU time, which it can schedule amongst its processes. That is 80% of the foreground are round robin. So here we can solve the problem with the round robin. 20% to the background in first come first served. In multi-level feedback queues, the process can move between the various queues. Means suppose if a process is starving again and again, we can, with the aging factor, we can move it to higher priority queue, right? So these type of queues are called multi-level feedback queues. Multi-level feedback queue scheduler has different parameters, number of queues for scheduling algorithms for each queue, method used to determine when to upgrade a process, method used to determine when to demote a process, and method used to determine which queue a process will enter when that process needs service.